Hello. Today we are covering improper integrals. These are integrals that involve an infinity of some kind. So in this case, that is not a circle. We have an infinity as the upper bound. So normally, I'm going to draw a really bad axis here. And here's our 1 y equals 1 over x squared. So for this integral, we're cutting it off at 1. That's our starting bound. So we're just calculating area, just like any other integral. The only difference is usually we have some kind of cutoff, but here we're just going all the way to infinity. So technically, we do have an infinite area, but calculus is weird, and sometimes we can calculate this. So something important going into these integrals. Sometimes you're going to get a number. Sometimes your answer's going to not make sense somehow. It's going to blow up. You're going to have some kind of undefined or dividing by 0, something like that. What's important is you don't freak out. It doesn't mean your answer is necessarily wrong. So basically just go through the following steps. If you get a number, great. If you don't, your answer still might be right. Don't freak out either way. As it turns out, if I put a 0 here, it would be a divergent integral, which means the answer is undefined. There is no answer. But if I have a 1 here, then it comes out normally. So I'll show both at the end to show you what it looks like, but we're going to do it starting at 1 first. So how do we solve these? In practice, you can already solve them, but technically you need to do the following. And it's really just extra notation. So what you're always going to want to do at first is rewrite your integral, but make a limit with a number. I made it, or a letter. I made it t. It can be anything. And sub it in for your infinity. So now we just have the same integral otherwise. And now you're just going to solve the integral as normal. So if I were to do that, we're going to carry around this limit, but it's not really going to matter. I guess I'll rewrite the integral at first to make it a little more obvious what I'm doing. And here we're just going to use our reverse power rule. Again, we're carrying around our notation, but it's no different. So now I'm going to evaluate the integral. We still have to carry around the limit. This comes out to x to the -1 over -1, reversing our power rule. And then we have from 1 to t here. Again, we're carrying around the limit always until you actually use it. So now let's evaluate that inner portion right here. We have our limit from t to infinity. I know my handwriting's really bad, but bear with me. So this comes out to -1 over x. I'll just rewrite that really quick. And then if we actually evaluate it, we get -1 over plugging in that t minus -1 over 1. And now, at this stage, once you've evaluated that portion, you've done your integral, all the normal steps. Again, nothing is new here so far. This is what's new. Now you have to evaluate your limits. So sometimes maybe you're going to have a more complicated limit where you're going to have to use L'Hopital's rule or something like that. Most of the time, which is the case here, you can kind of just plug in the infinity for t. And that's what I'm going to do. So I don't have to rewrite the limit anymore. I don't have to do that because I'm plugging things in. So we're going to get -1 over infinity minus -1. What is 1 over infinity? Well, that is just 0 in effect. So we end up with -1, which is just 1. So that is our answer. We've calculated the area under that curve. Again, it was something to that effect, cutting off at 1. So that area is equal to 1. This means that our integral was convergent because we got an answer. Now, what would have happened if it were 0 instead? So, for example, what if this was 0? Well, then we would have had a 0 here. And look what that does. Remember how I said before that if we did starting from 0, it would have been divergent, meaning we wouldn't get a numerical answer. That is how you know. We're dividing by 0, something doesn't add up, something doesn't make sense. We can't evaluate this. That's how we know that that integral was divergent, which basically means just uncalculable, unsolvable. The integral can't be executed. All right, that is pretty much it. Again, it's pretty much just solving integrals as normal, but we're just carrying around extra notation with these limits. We evaluate limits. You might have to calculate something, more complicated, where you have to use actual limit techniques, but most of the time it's just going to be, you can plug in your infinity, use common sense. If you get any number over infinity, that's just going to go to 0. If you get an infinity over an infinity, even if it has like a constant, like a 5 or a 7, whatever, a million, that's just going to go to 1. If you get infinity over a number, then that's infinity. That means your integral was divergent. Just use some common sense here with integrals and limits, and you should be good. That's about it. I hope that helped. You can put any questions in the comments.